Welcome to Module 5 of our course. In this module, we'll discuss web parameter tampering attacks. These types of hacking events occur when manipulated parameters are passed to script, for example through get or post, and affect the functioning of a service and lead to unpredicted script reactions. Critical information is commonly referred through hidden form fields. This is especially true of web applications integrated with external payment gateways. A malicious user may exploit this occurrence by intentionally modifying transferred data. If the information is not verified server-side, the functioning of an application could be affected. Let's take a look at a sample script designed to illustrate this problem. You can see here a page confirming the purchase of item number 1234. After clicking Confirm, the purchase will be executed, and a confirmation message will be displayed with the transaction price. Let's now see the HTML source code used here. As you can see, a form is generated which contains an item identifier, and surprisingly, item price. Let's try to change the values passed in the form. For this purpose, we'll use the Live HTTP Headers add-on. First, we need to intercept an HTTP request to the service and use the replay function to change the query and alter the values of the referred parameters. You can see here the content of the form referred by post, along with the price field. Let's try to change the value. As we can see, the price displayed by the script has been changed. If this information was not only displayed, but also used for other purposes, for example, transferred to a payment gateway or used to charge an account, a user could try to deceive the application and modify the amount paid. Remember that critical information shouldn't be made available to users. It has to be stored server-side. All information referred to users may be tampered with and modified by them. This is why it cannot be relied upon. Unfortunately, many websites still use hidden form fields to refer data to payment gateways. After a transaction is completed, they don't check if the actual transaction price equals the expected sum. If critical transaction data is passed client-side, its integrity should be verified by hash functions or other cryptographic mechanisms. That's all in Module 5. Thanks for your attention. In the next module, we'll focus on the path and information disclosure vulnerabilities. See you there. Welcome to Module 6. In this module, we'll talk about the path and information disclosure vulnerabilities. The vulnerability occurs when an incorrect script execution returns an error on a website, which reveals too much information to visitors. While this feature is helpful in developing an application or searching websites for errors, it may at times lead to an information disclosure that enables a hacker to see the full service structure and search it for potential weaknesses. Let's see a sample script which illustrates the problem. This simple script first connects to the database we've earlier created for this presentation, and then includes a second file, main.php. User input entered into the file is used to generate an SQL query that loads articles from the database. If the query is successful, the site will display the article. If it fails, the site displays an error message containing the SQL query which provoked the error. This might be helpful while building web applications. When visitors find errors, they can report it to administrators, making website building easier and faster. Unfortunately, a potential attacker may use the disclosed information to exploit other application vulnerabilities. Let's now see in practice how the script works. The database identifier 1 holds an empty article, so entering this path won't cause errors. What will happen, though, if we pass an invalid identifier, which will cause the SQL query to be syntactically and grammatically ill-formed? As we can see, the generated query is incorrect. 1a is not a numerical value and should be placed in quotes. If this error occurs, the content of the query is displayed. This dangerous revelation allows an attacker to realize that the service may be exploited through the SQL injection vulnerability, a type of vulnerability which will be discussed later. Moreover, the names of the fields and tables used in the database are also revealed to the hacker, which makes the potential attack even easier. Let's go back to our script for a moment. As you can see, we don't check if the ID parameter has been given at all. What could happen if this is not specified? It turns out that the PHP interpreter has returned more error notices. The messages disclose the number of the line, which contains the error and file name in the full path. If the file name is hidden through, for example, mod rewrite, the message will display the original name of a PHP file. This exploit may also reveal the service structure with directories, and, above all, disclose the path to the directory containing our web application. This could be exploited through a path traversal or PHP injection attack. As these types of data could be very useful for a potential hacker, it's essential to avoid information disclosure. Notice that the connection to the database is executed in index.php, while main.php assumes that the connection has already been set. What happens if the main.php file is launched in isolation? Both main.php and index.php are stored in the same directory, which is accessible by the user. As we can see, the execution of the script is not successful here, as the connection to the database has not been set. This results in more error notices. Let's think of how we may protect ourselves from these types of vulnerabilities and reduce the amount of output data when an error occurs. We may go back to the incorrect query discussed earlier. In that case, we could simply disable displaying SQL queries. While displaying them is a helpful feature for developers, the information should not be disclosed to all visitors. It's better to log the information into a file or only display the query after checking whether the current user has administrator or developer privileges. As you can see, the message has not been displayed now. Unfortunately, this does not solve the problem with returning error messages where no parameters are passed at all. It may be worthwhile to prepare yourself for all possible error scenarios. Errors may occur as a result of a user or service mistake. They may also happen as a result of a potential attacker testing the application for vulnerabilities. In such cases, our script could be called in a way which is not originally provided for. This is why it's useful to protect the application against at least several obvious problems. In this case, we could configure the script to check if a parameter has actually been given. The isSet function audits whether a given variable or identifier has been set. If it has not been set, an error is not returned. Instead, the value false is returned. As we can see, the error message has not been displayed. Let's now look into another scenario, launching main PHP in isolation. To demonstrate the process, we first need to get rid of the protection mechanism we've just implemented. As we can see, error messages are being displayed. We need to make sure that main PHP won't be launched in isolation. Here, you may enter a constant that signifies that the code needed for the script to run has been launched. For example, set the constant header run, which signifies that the code from index.php has been executed and may be utilized. The constant will be set in main PHP only if the file is included from within index.php. Let's see if this produces a change. As you can see, main PHP has not been executed at all in this case. We could also prevent the attack in another way. If the constant is not defined, the execution of script is blocked. If scripts are stored in another directory, you may try to use htaccess to quickly deny users access to these files. Reporting errors is also managed by the php ini configuration file. This is achieved through two variables: error reporting and display errors. Error reporting defines the types of errors which will be reported, while display error disables or enables displaying errors. If it is set to off, errors will not be reported. Let's switch it off. The Apache server needs to be restarted for the changes to take effect. Okay, as we can see, the code does not display errors. That's all in Module 6. Thanks for your attention and see you in Module 7, which will focus on forced browsing. See you there. Welcome to Module 7. In this part of the course, we'll introduce you to the concept of forced browsing. Forced browsing is not technically a vulnerability nor an attack. The term is simply descriptive of a situation where a user doesn't browse through web application resources by clicking URLs. but accesses content by manual identification of resources and may gain access to restricted parts of a service. Imagine a company that sends client emails linking to a page containing sensitive data like the client's personal information, account balance, and so on. This could look something like this. What's immediately striking is the identifier contained in the path. It's a numerical value and could easily be substituted for another parameter. As you can see, changing this parameter will display private information of another client. This could constitute a breach of the Personal Data Protection Act or lead to the leaking of valuable personal data of the company's clients. Another instance of forced browsing is the identification of vital service directories which store libraries, configuration files, and other files used to dynamically generate content. These files should be restricted from final users, as accessing them could lead to errors that result in leaking sensitive data or the script acting autonomously in ways that were not provided for by the application developer. If access to these files is not authorized in any way, forced browsing may also constitute an example of data hiding. Web developers want to restrict users from accessing files, but don't use any other methods of preventing this. In the case of web applications, developers often use common directory names to store service files. An example of such a directory is lib, which could contain library classes or full libraries used by a web application. Another directory is classes. You can also see here unsecured files, which, in isolation, could lead to displaying errors. Other examples are include and includes. The include directory doesn't exist in the service, but you can access the includes directory, which often contains configuration files. If the data is stored in a file whose extension is not linked to any interpreter, or the data is contained in INI or XML files, a user may be able to see the contents of the file and, for example, discover database credentials. Since the consequences of forced browsing could be very serious, you need to remember that while building a web application, you should never simply assume a visitor won't be able to access certain parts of the service. All directories have to be secured, and directories containing data which is only used server-side should be located outside the web server or blocked in an htaccess file. You also need to remember that incorrect file extensions could lead to the leaking of crucial data, like configurations or service source code. Finally, while displaying data to restricted groups of users, don't solely rely on line-generated identification numbers. It might be a better idea to use hash functions to generate less predictable identifiers. Better yet, be sure to implement cutting-edge authorization mechanisms in your application. That's all in Module 7. Thanks for your attention and see you in the next module, which will focus on path traversal attacks. Welcome to Module 8 of our course. In this module, we'll focus on path traversal. A path traversal vulnerability occurs where a user may alter the parameters referred to a web application to determine which files could be loaded by the application. Let's take a look at a sample source code illustrating the vulnerability. You can see here a simple website created in PHP. The contents of the subpage are loaded from a file stored outside the web root directory. As we can see, get is used to pass the name of the file which will be displayed. The file getContents function retrieves the content of the file but doesn't parse it. Notice that an attacker is able to freely manipulate the name of the file which will be displayed by the application. We can see here a website which is working normally. The address bar contains the variable site, which is used to specify a loaded file. Let's see what will happen if we submit the index.php file as a parameter. Take a look at the source code of the page. We can see here the source code of index.php. This is extremely dangerous, since an intruder may use the information to find other code vulnerabilities, or display configuration files that contain critical data like passwords to databases, mail servers, or FTP. Let's try to think of other ways in which an attacker could exploit this vulnerability. Insert the name of a non-existing file. The returned error information contains the full path to the page file. This is an example of a path disclosure vulnerability, which was discussed earlier. We also know that the web server of the site is Apache in the XAMPP framework. This helps us guess the location of the PHP ini. The string // passed at the beginning to the file getContents function in theory restricts the access to the current directory. In practice, by using standard special directories .. you may be able to navigate to parent directories. In this case, we'll climb 5 directories up. As you can see, the contents of PHP ini have been displayed. Using this method, you can access virtually all files stored in the web server, provided that their location is known and they may be accessed by a PHP interpreter. This is an extremely serious attack, which could lead to the disclosure and leaking of critical information concerning the server or the web application itself. Let's see how we can protect ourselves. Whitelisting consists of creating a list of files which can be accessed by a script and comparing the files selected by a user against the list. Another form of whitelisting is specifying the characters expected to be present in the inputted file name. If a user-provided parameter doesn't conform to the specifications of the whitelist, the file will not be read. Unfortunately, this solution is either impossible to implement or simply impractical. As you can see, in this case, an attacker even has control over the file extension. Let's try to predefine the extension. We'll modify the existing instances. After a restart, we can see that the extension has been added permanently to the end of the string passed to the file getContents function and may not be manipulated by potential attackers. In PHP editions older than 5.5.3, it was possible to pass the end of string marker %00, which was included without validation in the string passed to file getContents. This enabled an attacker to delete the added extension. The problem has been solved in newer versions of PHP. In a word, it's important to employ protection mechanisms to prevent hackers from reading restricted directories, even if we assume that the files with allowed extensions won't contain critical data. Filtering out the dot and dot// characters may also be useful. Let's now try to implement this mechanism. The function will delete the dot and / characters. Let's see if this is enough as a security measure. As you can see, all dot and / characters have been deleted, which certainly makes it harder for potential hackers to attack our application. Remember that there's always a risk present if users are able to modify application parameters to change the name of the processed file. That's why all input parameters must be treated with extra caution and be properly filtered. That's all for Module 8. Thanks for your attention, and see you in the next part of the course. Welcome to Module 10. In this part, we'll talk about the Web Parameter Delimiter vulnerability. This vulnerability occurs where a website utilizes a simple text file instead of a database for storing data server-side, and where the text file separates data with a specified delimiter. If the user-provided data logged to the file is not properly filtered, an attacker may be able to tamper with the structure of the database and, as a result, change the interpretation of the stored data. Take a look at this sample code of a website designed to illustrate the problem. You can see here an example of a database file. The first field in the database represents username. The second field represents password. The third, email address. And the fourth field specifies a user type, a user with administrator privileges or normal user. Now let's take a look at a file used for registration in the service. As we can see, a simple form is displayed for user-provided data. Next, a file is opened and the input is written to it. The data is separated with the same delimiter we've previously seen in our database. Finally, the field normal is added, which specifies the user has normal privileges. You can also see here a login script which loads the entered login and password. You can also see here a login script which loads the entered login and password. If the following login and passwords are entered, a database file will open. The file will be separated into more lines via the file function. The function explode separates each file line into different fields. The login and password provided by a user are compared against the stored credentials, and if matching data is found in a line, an appropriate message will be displayed. Next, user type is verified and reported. Let's see how this works in practice. You can see here a login form. Enter the login and password of an existing user. As we can see, the user administrator is logged in and recognized as a user with administrator rights. Let's try to register a new user. Use regular for the username and user for the password. The registration has been completed successfully. Let's take a look at our database now. As we can see here, the information we entered into the browser has been added to the database. Let's try to log in now. As we can see, the login is successful. Now let's go back to the registration form and try to make use of our knowledge about the used delimiter and the database structure. Register the user hacker with the password hack. And the following email address. Add the delimiter character and type in next to it the marker which specifies administrator account. The registration is successful. Let's see what our database looks like now. As we can see, the data in the first fields has been logged normally. But other fields contain the added delimiter and injected administrator identifier. As we see that index.php only loads the first 4 fields, this probably means that the record will represent a user with administrator privileges. Let's try to see if this is true. As we can see, the user is logged in and has administrator privileges. How can we protect ourselves against this attack? The core of the problem lies in the fact that input may contain an injected delimiter, which is used in our database. This could be solved by adding the strReplace function, which serves to delete all delimiters from user input. Let's register a second user now. Use the prepared string. Let's take a look at the database now. As we can see, the delimiter has been cut out and the structure of the database has not changed. In order to confirm this, log into the service. As we can see, the attack has failed this time. That's all in Module 10. In the next module, we'll focus on PHP injection. See you there.